Okay, good evening, everybody. We're super excited for today's session, today's webinar. So we are also streaming this. I know we have all our Developers Learning Club leads on our Hangout. We are also streaming this via Twitter, through Periscope, and we also have a stream going on YouTube. So we're going to take questions. We're going to try to get all those questions answered. So before we jump into everything, I want to give you a quick introduction. My name is Madhusha Kure. I'm with Google Developer Relations, and I'm responsible for supporting and running events with our Developer Student Clubs. So Developer Student Clubs is a community initiative that we backed from Google, where student leads are selected to run student clubs on technology backed by Google across North America and the globe. I'm just responsible for North America right now. So we have guest speakers coming in. We have workshops that we run. Also, we're going to share the link. If you are interested in becoming a developer student lead, we can share that application process as well. That being said, I want to switch to our guest speaker today. Now, Tanmay is a fellow Canadian, just like me, from Toronto. And he is also an advocate with IBM. He's working there right now as an intern. Tanmay is also one of our Google developer experts. So this is one of our other programs that we support, where we bring in technology experts to bring in as speakers to engage. He's been talking and running workshops for hundreds of thousands of people over the years. So welcome, Tanmay. Awesome. So when I announced the event, the biggest question I got was, is it really 15?
So, well, yes. I mean, technically, I'm now 16. So as of October last year, I'm now 16 years old. But yeah, I've been working with technology for the past couple of years, and specifically for the past like 5-6 years, my main focus has been on machine learning and artificial intelligence technology, really all sorts of next generation technologies. And yeah, it's something that I'm very passionate about.
So you just got your driver's license, I'm guessing.
So actually, the fun story behind that is I was going to get my driver's license on my birthday, but then there was a conference on the day of my birthday, so I had to like fly on the day of my birthday to Chicago for a conference. And then by the time we got back, unfortunately, like there were so many different things to do, I didn't get the chance yet. And then unfortunately, the whole COVID crisis, but soon I will.
It's interesting how you prioritize it, whereas another teenager would be like, yeah, I'm going to go get my license. This is awesome. So the other question before we jump into our session is that, so how did you get started at such a young age? How did you become such an avid expert in the subject area?
So really, I mean, initially I started working with technology about 11 years ago, back when I was like 5, was when I first started getting fascinated by technology. And back then, really what drew me to technology was the fact that, I mean, at the end of the day, for a 5-year-old, everything is a toy, right? Everything is just something that I'm playing with. But what really fascinated me about technology in specific was I could interact with it in infinitely more ways than I could essentially anything else. And that really just made me curious. That really piqued my curiosity. And so my dad saw that curiosity, so he introduced me to like the world of programming and technology, but my curiosity only kept growing. And so I started to use the internet and different books to learn even more about the world of tech. So I started to learn different languages like Objective-C. And I, in fact, actually had my first iOS app released onto the store when I was 9. And that app was actually initially meant just for me, to help me practice my times tables back in grade 3. But eventually, I decided, hey, well, obviously I can create software, so why not create software that helps others as well? So I released that app, and then I noticed, hey, not only can I create software, but I can even create content that helps people create their own software, right? So then I started my YouTube channel. So it's sort of like one thing led to another, and sort of growing that organically. But it initially started as just, I was fascinated by technology. I loved playing with it, so I thought I might as well figure out what goes behind it. Because if I could figure out what goes behind it, I could control it myself.
That's amazing. And I mean, kudos to your parents for helping you and letting you follow your passion. But that must have been an interesting challenge for them, to see and let you do that, at the same time think about what your future would be and how you should be educated. what was that like? So were you homeschooled or did you go to school? Tell us a little bit about that.
Sure. So, I mean, for the past couple of years, I have actually been homeschooled. And really, the reason that my parents came to that decision, it took multiple years to make that decision. But the reason that they came to that decision eventually was because they realized that learning for me was generally more effective if it was done in a more organic way. And when you're homeschooled, that organic sort of method of learning is afforded to you. So, like, I mean, one thing eventually leads to another in the way that I like to learn. It's like I can learn at my own pace and in my own sort of way, which I wouldn't necessarily be able to do without that. So yes, I have been homeschooled for the past couple of years, and that's definitely something that I'm passionate about. As a matter of fact, actually, now that we've touched upon the topic of education, homeschooling is something that we all technically have to kind of do now because of this whole COVID crisis.
Yeah, that's true.
And so actually I have a webinar that I'm hosting on Sunday. So that will be May 24. And it's actually the 4th episode in my Tech Life Skills with Tanmay series that I host. And we're going to be essentially talking about education, and I'm going to be asking questions and discussing with world leaders really in the field of education, really getting their global perspective on how education is going to evolve. So that's something that I'm passionate about. But yeah, you're right. It was a difficult decision for my parents to make, but we made it because I felt like that organic learning was more effective for me.
Awesome. I think we would love to hear about that. I'll definitely share that as well with the rest of the community. That being said, I'm going to hand everything back to you, the expert, and teach us about the fundamentals.
Sounds good. Thank you very much, Madhusha. I'm really excited. I'm going to go ahead and share my screen so you can actually take a look at the content that I've got prepared. And there we go. All right. So thank you very much, everybody, once again for joining the live stream. I really appreciate it. And I mean, as Madhusha mentioned, my name's Tanmay Bakshi. And really my passion for the past couple of years has been to explore the world of next generation technology and working with technologies like artificial intelligence and machine learning, researching, developing new tech, and at the same time applying it in fields where I believe it can make an impact. So fields like healthcare or education. And not only developing this technology is what I'm passionate about, though, I'm also very passionate about enabling people to use that technology for themselves as well. And so for the past couple of years, I've been working towards really reaching out to as many people as possible through a variety of different media. So for example, through the 3 books that I've authored and that were published just last year, actually, on my YouTube channel, where I've been uploading tutorials for the past couple of years on all sorts of topics, from machine learning and artificial intelligence to math and science and programming and all these sorts of different topics. And so today, of course, we're going to be talking about machine learning technology, and I'm going to be introducing you to essentially the basics and the fundamentals of this machine learning tech and how you can get started with the TensorFlow framework. Before that, though, I do want to say a huge thank you to the Google developer expert community for putting this together. I really appreciate it. I'm excited to be doing this webinar, really. And also another huge thank you to Madhusha for inviting me and setting this up. Again, it's really exciting to be able to do this talk on the basics of machine learning technology from the ground up. In fact, this is going to be a series. We're going to have multiple episodes of this, getting more and more advanced based off of what you want to know. Again, keep all your questions in the live chat, and whenever we feel like there's something relevant that we want to answer, we'll be getting to that as well. But we will have a dedicated Q&A round at the end too. And so to really dive right into what we're going to be talking about today, I feel like it's important to answer a more fundamental question, and that is, what is machine learning in the first place? And a lot of us, take a look at these incredibly complex examples of machine learning in action, and it looks like magic almost. I mean, you take a look at things like Google Assistant and all the different machine learning powered components, the speech to text, the text to speech, the natural language understanding that's going on. You could take a look at Google Maps and how they're using machine learning technology for their routing. You could take a look at Gmail and how Smart Compose enables you to communicate faster and more effectively. And there are all these different examples of machine learning technology. But I feel like when you boil away all of the complexity, machine learning at its core, the basic concepts, are actually really, really simple. In fact, they're so simple that you probably wouldn't believe just how simple they are. Really, at its very core, machine learning is all about one thing: you have two data sets. Let's just call them X and Y in this case. And you know that there's some kind of causal link between X and Y. So some kind of change in X will create some kind of change in Y. And there's a link there that makes that change occur. But the problem is, even though you know that link exists, you, as a human, you can't find what exactly that link is. Now, why you can't find that link, there can be many different reasons. The data could be too complex. There could be too many features in the data for you to analyze. There could be too much data in the first place. But essentially, the issue that we're dealing with here is that you've got two data sets. You have to somehow figure out a mapping between X and Y such that you can take a new X that you've never seen before and predict what its Y will be. But the problem is that you can't do it yourself. You somehow need the computer to help you find that mapping automatically. Now, this could be, for example, a simple little classifier where you want to measure a couple of attributes of a certain flower and try and classify what species it is. Or it could be a lot more complex, and you could be taking audio data and transcribing the individual phonemes from within the audio. So there's all sorts of things you could do in this vein, but if you were to boil it down, it is about taking some input data and predicting some output with some series of mathematical transformations in between. And I'll be getting deeper into what those transformations are and what they look like in a bit as well. But first of all, just to sort of give you an idea of what we're going to be going through today, I do want to start off by sort of just introducing you to some of the basic math behind machine learning. And then from there, we'll go ahead and implement that basic math in TensorFlow. And then I'll give you a bit more of a complex sort of orchestration of that math through an example called trilateration. Before we begin, I will say that today's talk is going to be interactive. So if you want to follow along as I write any code, feel free to do so. If you don't already have TensorFlow and this environment set up locally, feel free to go to labs.cognitiveclass.ai, sign up for an account. It's totally free, and you will be able to have a Jupyter Lab environment with TensorFlow already installed, so you can get up and running immediately and write your code. You can do all sorts of things, plotting and everything from directly within the notebook. Apart from that, the actual trilateration notebook that we're going to be getting into a little bit later in today's webinar is at the following bit.ly link, and we will take a look at this more when we need to in a couple of minutes. But first of all, labs.cognitiveclass.ai, you can start signing up for an account now. In the meanwhile, I do want to cover a little bit of the math behind machine learning technology. Now, of course, the point of this isn't really to teach all of the math. I'm not going to be teaching you the individual techniques or how that math actually works, but I will be giving you an intuition for the math behind machine learning, the important parts. And I feel like a great way to start would be to even just plot out a simple function. So for example, let's just say we've got sine of x. Now, just to sort of get a certain, there's one concept that I want to sort of explain first, and that is the concept of derivatives of a function. So assume we've got a function like sine of x, and we want to find the derivative of sine of x. Well, here's the thing. We don't need to do that. We're within a calculator right now. And in order to find the derivative, all we would need to do is find d over dx of sine x. I'll explain what this means in just a moment. But I don't want to gloss over just how important what I just did is. What I did is I just told the calculator to essentially find the derivative of this function for me. Doesn't seem like it's very important now, but when we start getting into TensorFlow in just a bit and how it makes your life hundreds of times easier than it would have been just a couple of years ago, you'll start to see just why it's so important. But for now, let's get back to this math that I was talking about. So let's go ahead and hide this derivative, and let's just take a look at this function. Now, as you can see, this function, this wave over here, this wave gets steeper and flatter at different points. So over here, for example, the wave is quite flat. It's not really changing very much. But over here, it's really excited, and it's very steep. That line is very steep that it's drawing over here. So in a way, what you could say is that the rate of change of the function is slower here, it's slower here, whereas it's a higher value over here. And over here in the middle, the rate of change is positive. That means it's going up with time. But over here, it's negative. So it's very steep, but it's negative. It's going down. right? And over here it's flat. And that's how you can think of something called the rate of change. And what the derivative does is it's a more formal definition of that rate of change, right? So instead of just looking at this graph and saying, all right, the steep point is over here, the derivative actually helps you encapsulate what that magnitude of how steep the function is at that point actually means, and also the direction in which it is ascending. So if I were to unhide this little line over here, as you can tell, we are starting to see what I meant by that rate of change. So over here, where the function is super steep, this derivative function peaks because, well, we're growing fastest here, so the derivative, which is the rate of change of the function, is going to peak because the original function is changing quickest at that point. Whereas over here, where it's quite flat, the derivative function has a pretty low value. And so that's sort of what the derivative function tells you. It tells you at a certain point, how fast is the function changing, and also in which direction is it changing. So as you can see, for example, here, the derivative gives you a positive value, +1, whereas over here, it's going to give you -1, and it gives you -1 because we're going down. And so the derivative is going to tell you the instantaneous rate of change. Now, whether or not instantaneous rate of change physically makes sense as an analogy to the physical world, that's a topic for, again, a whole separate webinar series. But for now, that's all you really need to know. But there is one more thing I want to tell you, though. There's another way to think about the derivative. And that is that not only is it the rate of change, it gives you a trajectory that you can follow in order to increase the value of the output of the function. So think about it like this. At this point over here, we can see that the function is increasing positively. So if the x value fed into the function were to increase, then the output of the function would also increase. So we know the direction in which the function is ascending steepest. And we also know the magnitude. We know that it's 1. That means it's going quite steeply because comparatively, that seems to be the peak of this function. So we have two pieces of information from this derivative. In which direction are we ascending most steeply, and what's the magnitude of that ascent? And so with that information, you could technically continuously modify the value of x to make it reach a certain maximum or minimum point of the sine function. So for example, if x was over here and you wanted to reach a peak on the sine function, then you would ask the derivative, all right, which direction do I move in order to increase the output of sine for a new value of x? And it's going to tell you move positively, and you'll increase x by some value. And you're going to keep doing that until you hit this peak, at which point the derivative is telling you either don't move, or if you overshoot a bit, the derivative becomes negative. And when you add that negative value to x, oh, what do you think? Well, you come back because you want to go back to that peak. So the derivative is, in a way, a trajectory that you can follow to get to the steepest point of that function. And here's the fascinating part. If you negate the derivative, which obviously is quite simple, just by doing this, then suddenly the derivative is pointing the other way. It's pointing in the direction of steepest descent. Now, if you follow it, you're going to get down to a value like this one. And so that's sort of how you can think of the derivative of a function. Why is that important, you may ask? Well, let's figure out why it's so important. So I'm going to go ahead and hide these two. If you want to go ahead and sort of take a minute to think over that logic and that intuition, feel free to go to the Desmos calculator and actually try it out. But for now, though, I want to move on to another topic, and that is the perceptron. The perceptron is the basic building block for all modern machine learning and deep learning algorithms, almost all, as I would say. And the perceptron is actually really simple. Let's go ahead and implement one right now. A perceptron takes an input, and it takes a parameter called a weight. The weight can be adjusted to be whatever it needs to be, such that when you feed in some input, the perceptron will give you the output that you expect. The way the output is calculated is simple. It's just the input times the weight. That's all there is to it. That's the perceptron. Now, if there were multiple inputs, then there would be multiple weights, each weight corresponding to a certain input, and you would calculate the weighted sum of the inputs. So each input will be multiplied by a weight, and then you would calculate the sum. And right now, let's just say I wanted to create a perceptron where I can feed it some input and it'll return the negative input. So if I feed it 2, I want -2. Or if I feed it -105, I want +105. Now, as a human, intuitively, you can really easily say that the weight should be -1, because obviously when you multiply 2 by -1, you get -2, or -105 by -1, you get +105. As a matter of fact, if we were to go ahead and plot this out, you can see that this graph is just x times -1. So wherever you go on this, the output of the function is going to be the negated input. So for example, at x equals 3, the output is -3, and vice versa. For -3, the output is just a +3. And so, as you can tell, this function works. But here's the thing. You're a human, and for a single value, it's easy to determine that the weight should be -1. But what do you do when you have hundreds of dimensions or hundreds of data points that you want to take a look at? You cannot graph that out. So you need the computer to figure out what that weight should be mathematically. You want to be able to have that as a knob that the computer can turn and find exactly where that knob should be in order for your output to be what you expect. So how about this time, instead of graphing x as the input, let's graph x as the weight. So let's just say the output or the input is 2, and the weight is x, like so. Well, then you can see when the weight, which is x, is -1, then we have the output that we expect, -2, and that is exactly what we want. But here's the thing. For other values that aren't -1, how do we quantify just how bad that prediction was from the perceptron? Well, to do that, we use something called an error function or a loss function. So what that's going to do is it's going to take our input and our weight, but also the output that we expect, and it's going to return the loss or the error at that point. So in this case, we're going to implement something called squared error, which sounds pretty fancy, but it's really just you feed the data into the perceptron, you remove or you negate the output that you expect, and you square it. That's it. So it's positive. Now, if you take a look and we plot out the loss where the weight is x, and let's just say we feed in a 2 and the weight is the x coordinate, but we expected a -2, then as you can see, the error function's lowest point is at -1. Because when the weight is -1, then it's a perfect prediction, right? So the error is 0. There was no error that the perceptron made. Now, again, as a human, you look at that point, you're like, it's -1. What else do we need to do mathematically? But for a computer, it's a bit more complex than just looking at the graph. So then we're going to have to find the derivative of the loss function. And I feel like you can see where this is going. If we find the derivative of the loss function like this, watch this. Now we have another line, and this line is going to point in the direction of steepest ascent for the loss function. And when we negate this value, suddenly we have a function, or we have a line really, that's pointing in the direction of steepest descent. Now we just follow this line until we hit the minimum point of the loss function, and when we've reached it, we know that we have the perfect weight and we can make predictions correctly. But there is a bit of a problem, and we don't need to get deeper into why this problem exists right now. But as you can tell, this green line is really steep, right? And that can be a bit of a problem, because let's just say you're over here and you want to step. It's possible that as you make your steps, you end up overstepping and you go past that minimum point, and now you're increasing in value again. And then the derivative is going to point you back, and you're going to go back. And you're going to keep oscillating around that point until you either hit it or you just keep infinitely oscillating around it. And so what you would usually do in order to solve this problem is multiply this negative derivative by something called a learning rate, which defines how fast you want to learn or how big you want your steps to be. In this case, let's just say 0.01. As you can see, not nearly as steep. And what this makes you do is take smaller, more calculated steps toward that minimum, and right as you reach it, problem solved. You no longer need to do anything. And by any chance, if you're starting off on the other end, well, you just move in the other direction, because the derivative is giving you not only the magnitude, but also the direction in which you need to move. And so this is why derivatives are simply amazing. You can use them to optimize a function to reach the value that you want them to reach. And so now that we understand a little bit about derivatives, how exactly does this relate to the world of TensorFlow or machine learning? Well, what I've shown you right now is just a single perceptron, but you can layer hundreds or thousands of these perceptrons together in order to create a more complex neural network system. But we'll talk about that in just a moment. First of all, let's talk about how you can implement this exact same number negator, so this is exactly what we've done in Desmos, within TensorFlow. So in order to do that, I would recommend you open up Cognitive class right now, so you can go ahead and follow along with the lab as I run this code. Now, Cognitive class comes with TensorFlow 1.8 installed, so I would recommend you run pip install TensorFlow 2.2 so that you can get the latest version of TensorFlow. Now, here's what we're going to do. This is going to be a super simple example of TensorFlow in action. There's nothing going to be really fancy here. It's just going to be a couple of lines of code. So the first thing is, of course, classic Python, you've got to import TensorFlow, like so. Once we've imported TensorFlow, then we're going to create something called a TF function. Now, this technically isn't necessary for you to write. You don't need to write this right now. But it helps with performance, and we'll talk more about it in a future session. And I'm going to create something called the error function, or you could call it the loss function if you'd like. It takes an input, a weight, and an expected output. And all it's going to do is it's going to return the prediction minus the output, and then we're going to square that difference between what we actually predicted and what we actually expected. There we go. We've got the loss function. Now, if you wanted, you could just go ahead and feed in some values. So, for example, you could feed in 2, 0.5, -2, and you can see that your loss is 9, which should correspond correctly to what you find on Desmos. But the thing is, we want to optimize this weight. So what we're going to need to do is convert this weight to what's called a tensor. And a tensor is the kind of value that TensorFlow can actually work with. We'll get into more detail on what exactly tensors are and how they work internally in a later episode. But for now, all you need to know is that we're going to create a weight, and we're just going to tell TensorFlow to convert, say, 0.5 is our initial guess, as a 32-bit floating point value to a tensor. Just like that, it's just simply wrapping that scalar value. Okay, so it's still 0.5. It's just a new kind of 0.5, a tensor value. And now what we're going to do is actually quite simple. And this is, again, the incredible part of TensorFlow. We're going to create something called a gradient tape. Now, this is a bit complex to describe, so let me quickly write this code, and then I will tell you exactly what it means. So let's just say we want an input to be a constant, and let's just say we want it to be 2, and we want that to be a 32-bit floating point, and we want our output to be -2, but of course we've got to pass our weight. So just like that, we should be able to print out tape.gradient of L with respect to weight. Okay, so what I've just done over here is I've created something called a TF gradient tape, a TensorFlow gradient tape. A gradient tape is essentially just a little data structure within TensorFlow that will watch certain tensors. And whenever you run an operation on that tensor, it's going to note that down, and it's going to continuously log them in memory. It's going to create a graph of those operations. And then, here's the interesting part. When you're done whatever operations you need to do, you can actually go ahead and tell that tape, hey, see this value? Give me the gradient of this function with respect to this value. And it'll go back in its log of all the operations that you did, and it'll actually automatically calculate that derivative, or in this case, we're calling it a gradient. Derivative versus gradient, really, it's just a simple distinction. A derivative is just a single variable that you're finding the derivative with respect to, whereas a gradient is just a tuple of all the different variables that you're finding the derivative with respect to. In this case, we're just using the gradient terminology because that's what TensorFlow and machine learning frameworks use because of the way that they work and because of the way neural networks are structured. However, what we're basically doing here is we are finding the derivative of the loss function with respect to the weight that we are feeding into it. So when we tell the tape to watch the weight, then when we feed that weight into the loss function, it's saying, hey, you multiplied this constant by this weight, note that down. Then you took that value and you ran that value minus output, note that down. And then it's noting down that you squared that. And then when we ask for the gradient, it's going back through all that, is using a bunch of vector Jacobian products to do back propagation and figure out that, hey, this is supposed to be the derivative function, and I'm going to calculate that derivative, calculate that gradient, and then return it to you. In this case, it's returning 12, which is, of course, the correct answer. Now, if we were to step by 12, you can imagine just how off that would be. If we were to do 0.5 minus 12, that would bring us to negative 11.5. We don't want to step that much. So we're going to scale our step by a negative learning rate. And that learning rate, let's just say 0.01. And of course, we want that to be a 32-bit floating point. And just like that, now we've got a super small step. And in order to optimize the weight, we can just do weight plus equals this little step that the derivative is giving us. And then we just repeat this, like, say, 100 times. And each time we can actually print out the weight. And watch this. What's going to happen is we're going to slowly see that the weight is converging to -1. Now, if you were to continue this a couple hundred more times, obviously you would get better and better and sort of closer and closer to -1. But we don't really need to be that precise. It doesn't matter that much in machine learning. So now if you were to calculate your loss, you would actually see an incredibly low value, very, very close to 0. As you can see, incredibly close to 0. And so that's the number negator in action. Essentially, what we just did here is we implemented the simplest and most basic unit of a modern deep learning system. Now, again, if you were to stack hundreds of these, you would be able to get much more complex behavior, and we'll be talking about this complex behavior in just a moment. And so that's number negator. Next up, let's talk about another example. And this one is really, really interesting. It's called trilateration. Now, trilateration is the way that GPS works. You're probably wondering what I mean by that. But if you study how GPSs work, you would know. And that is that, let's just say we've got this graph over here. You're somewhere on this graph. You're somewhere on this grid. You don't know where you are, but you do know that you have 3 friends. And you know exactly where they are. And you know your distance to each one of those friends. Now, based off of that information, how can you determine where you are on the graph? Now, on a graph, it's super easy. All you do is you draw circles around your friends, where the radius is the distance between them and you. And wherever all 3 of those circles intersect, well, that is where you are. And just like that, we know that the point that we're referring to is at 2, 2, with the following distance values that are coded into the calculator. But here's the thing. If you were to mathematically calculate this, you could either do it the linear algebra way, which is the way that you would use it, that you would generally do it on a graph like this one. Or you could use gradient descent in order to optimize a guess. Now, what we're going to do in this case is we're going to be using gradient descent to optimize a guess. And technically, in the real world, you wouldn't necessarily want to do that because you can do it more precisely with algebra. So for example, GPSs obviously use algebra. But in this case, in order to understand and appreciate the value of TensorFlow, we're going to be doing a gradient descent version of this example. So think about it like this. Let's just say I were to say, I'm guessing that I'm located at 10, 10, but I'm actually located at 2, 2. So that's quite far off. A way for me to determine how far off I am would be to determine the distance from 10, 10 to each one of the friends, and then take those distance values and compare them to the distance values that I know. The distance values that I know in terms of how far away you know you are from your friends. And based off of the difference, based off of the error between the perceived distances and the distances that you know are true, you know how far off your prediction is. And when you find the derivative or the gradient of that function with respect to the guess coordinate, you can optimize that guess to get closer and closer to where you actually are on the graph. I've already gone ahead and written out the code for this over here. There should be a link in the YouTube live stream chat with the notebook. But in case you don't have it, you can see it over here, bit.ly/trilateration_Google. And essentially, this notebook will give you the code that you need to implement the trilateration example that I was just talking about. Now, again, since we're running on cognitive class, you'll need to install the latest version of TensorFlow. But apart from that, as you can see, this is an example of trilateration. What I'm going to do is I'm going to quickly clear all my outputs just so you can take a look at this notebook fresh. Of course, as with every other Python script, we're going to have to start off with some imports like TensorFlow and Matplotlib and NumPy. And here's what we're going to do. We're going to implement that error function that I was talking about. But we're going to need 7 pieces of information. First of all, I need to know where the 3 reference points are. These are the points that we know the locations for. Then I need to know the actual distance from yourself to each reference point. These are the distances that we want to have. Then I need to know the guess point. And the guess point is where we're guessing that we're currently at. Now, based off of that information, I'm going to calculate 3 values. I'm going to calculate the distance between the guess and the reference coordinates. And I do that this way, using Euclidean distance, which is basically just the square root of the sum of the square differences between each individual coordinate. So, for example, you can do an element-wise subtraction between the reference point and the goal, square that value, sum those squared differences, and then find the square root. And that's your straight line distance, your Euclidean distance. So I find those 3 distance values, and then I compare what we perceive as the guess distance versus the distance that we expect. And I find those squared error values, just like we did with the number negator. And then I just find the average of those errors, and that's our error. It's that simple. That is called the trilateration error. It looks complex at first sight, but really when you boil it down, it's quite a simple function. And then I'm just going to put together a couple of values. So for example, let's just say these are my 3 reference points over here. So R1, R2, and R3, just like they were over here in Desmos. So R1, R2, R3. And then I have the distances that I expect. So those would be D1, D2, and D3. And then I've got a guess point. The guess is just 100, 100, which is totally off from where it actually is. And so I'll make it a slightly better guess just for visualization purposes, and then we'll make it bad again. But we're starting off at 0, 0. Right, so we start off at 0, 0, and our goal is to optimize it such that we end up at 2, 2, because that's where we're supposed to be. And our learning rate is 0.3. So unlike the number indicator, we have a slightly higher learning rate this time. So I'm going to go ahead and run that code. And now this is basically just the code that we had for the number negator that would do the actual optimization, just put on steroids, essentially. So what I'm doing is I'm storing something called an error, which starts off at infinity because we haven't calculated it yet. And I'm saying, you know what? While the error isn't within the margin that I want it to be in terms of precision, just keep going, keep optimizing. And so what that means is that until the error is lower than 10 times 10 to the power negative 10, we're going to continuously optimize that prediction. So we start off, of course, by creating a gradient tape, and that gradient tape is only going to watch the guess. And then we calculate the error. So just like we did last time, we're calculating the error. And it's simple, but we're just passing in some more data. So we're passing in the 3 reference points, we're passing in the distance values, we're passing in the guess. And then when we have that info, we're just printing out, okay, here was the error. And that's just so that we can see that in our console. And then I go ahead and calculate the gradient. So the gradient of the error function with respect to the guess that we have. Now, of course, once again, what did I tell you? The gradient is pointing in the direction of steepest ascent. It's giving us a magnitude and a direction that will help us go up, but we want to go down because a lower loss, a lower error is better. So what we do is, in order to smooth that out a bit, in order to make it a little bit less intense, we multiply it by a learning rate, but that has to be a negative value so that we end up going down and not up. And so we just go ahead and add that to the guess, and just like that, we're done. Just a little bit more housekeeping work. I am taking that guess and appending it to an array so we can see all the guesses over time. I'm going to go ahead and print out the guess and update the error value so we end up stopping the while loop eventually. So now if I go ahead and run this, as you can see, TensorFlow is so fast that it was practically instantaneous. Towards the end, we can see both values are converging to 2. And here's the fascinating part. I can go ahead and plot out what that movement looked like. And so, as you can see, the green points are our reference points, and the red started off at 0, 0, but slowly moved into the 2, 2 position, which is where we actually are. So if you were to visualize like a 3D surface plot of the loss function, you could think about it as like a little basin at 2, 2, and then it just increasing and getting larger and larger and flatter towards the outer sort of edges of the surface. But towards 2, 2, it suddenly shrinks quite fast and hits a 0 value when you're at exactly 2, 2. And so just like that, you can go ahead and take a look at that scatter plot of how this trilateration example moved over time. Now, what's really interesting is you can actually modify the initial guess to say something completely off, like 100, 100. And as you can see, it takes barely any extra steps to get to the correct location, because remember, the gradient is not just telling us the direction, it's telling us the magnitude. And so the first step from 100, 100 to the next point was huge. Take a look at that gap. But then from there, it got smaller and smaller in terms of step sizes until eventually we started to move into that 2, 2 position. And as you can see, it still did converge to 2, 2. And so this is the basis behind machine learning. Everything you see that's powered by deep learning technology is nothing more than this technology but scaled up to maybe not, in this case, 2 parameters, maybe millions, maybe hundreds of millions, maybe billions. It really depends on the individual use case and why that machine learning technology is being implemented. And so that's how this technology works. This is the trilateration example behind TensorFlow. Now, before we continue, I would love to see if we have any questions from the live chat. So anything, Madhusha, do you think we have anything that we want to take a look at right now?
Yeah, let me open it up to everybody. Also, we have some DSCs live right now. Anybody want to unmute and ask any questions? Welcome to do so.
That would be great.
Hey, Tanmay. Just a quick question on one of the kind of the 2-2 endpoint we were trying to approach. I saw how we had different locations. I was just wondering where exactly we kind of state the expected location of the machine learning. Like where are we saying, like, this is what we expected you to guess versus what they actually guessed?
So that's the interesting part. In this specific example, the entire point is that we're not explicitly stating what that expected value is. And so when we're converging to 2, 2, the reason we get there is because we know the distance from 2, 2 to the reference points, and we know the distance from our current guess to the reference points, and we're trying to optimize it such that those distance values are the same, and by proxy, we end up finding where we are. So that's this is again sort of the GPS problem. You don't know where you are on the planet, but GPS satellites know where they are, and you know your distance to the GPS satellites, so that way you can determine where you are on the planet.
Okay, so would each guess then, feeding in that same error, it sees that it's getting closer and closer to that approximate correct value?
Exactly. So using the gradient, you step the guess towards 2, 2 or towards where it thinks is the correct value, and you continuously optimize that and feed the previous iteration back into the next iteration over and over again until you end up at where you expect to be. Right. Any other questions? Maybe something from the live stream or anybody joining in? Or we can move on to the next example.
Okay, so I'm going to take one from YouTube.
Sure.
Is there a G point? Is there a G point vibrate around 2, 2? Maybe. Is 0.3 too big?
Sorry, I'm not sure if I got the question. Are they saying why it's not precise at?
Okay, so I think that Longfei, please add some context to that question on the comments. So let me take another one. To what extent do you think we should learn mathematical concepts in fields like linear algebra before we approach building ML applications?
So I would say that, again, because of the way artificial intelligence or machine learning has evolved, nowadays, when you want to implement technologies that are relatively simple or that use pre-existing architectures, you don't need to have a very strong sort of mathematical foundation to do so. AI has been democratized to the point that you could even use services like Google's AutoML in order to implement machine learning algorithms for you. So you don't technically really need to. But then when you're doing research or trying to develop new techniques or new algorithms, that's when this starts to become important. Because at that point, in order to invent those new techniques, it's useful to know the mathematics that go behind it. So from an introductory level, to work on basic examples, you don't really need to know that sort of mathematical foundation, although it does help when you start to get to more complex architectures and research, or just generally customizing things to work for your specific use cases. So here's what I think we'll do. I do have one more thing that I want to show today before we continue answering more questions, and then we will move on to answering more questions.
Sounds good.
All right. Great. Okay. So now there is a bit of an analogy that I want to give you really quickly around the world of machine learning technology. And before we get to that analogy, there's a little demo that I want to show everybody, and that is called the TensorFlow Playground. So I want everybody to open this up. If you'd like to sort of follow along, you can do so at just playground.tensorflow.org. And the TensorFlow Playground is pretty amazing for just learning the basic concept of how these perceptrons interact with each other. Because watch this. In the TensorFlow Playground, you can develop a neural network like what you see in the middle of my screen right now. And you can take a look at what kinds of relationships it models on the right over here. So on the right, there's a bunch of data points, right? And these data points, they're either blue or they're orange. And the point is that the neural network is going to try and classify these points as either being orange or blue. Currently, as you can see, the network isn't doing a good job. The background color of this graph is the network prediction. It's not particularly doing well because we haven't trained it. We haven't done any of the gradient descent that I was talking about. And watch this. With the power of the TensorFlow Playground, all you need to do is click the play button, and there we go. The TensorFlow Playground is now training the network for you. And if I go ahead and pause, as you can see, it's got a very good fit. It's 100% accurate in training cases. And so as you can see, there's just a little white line that's separating as sort of like a decision boundary between orange and blue, but it's able to successfully model the relationship between this sort of orange category, this orange territory in the graph, and the blue territory. And the reason I'm showing you this is because what you're seeing right now is a linearly separable data set. And so what that means is on this data set, you could just draw a straight line, and that one straight line would separate two clusters of data. Now, to classify or to process data like this is trivial. It's super easy. You don't even need a neural network for this. You could just use simple linear regression. And in this case, a single perceptron is able to model this linear relationship. All it's doing is it's taking two input features, which are either -1 towards the left of the graph, +1 towards the right of the graph, and also another feature which is -1 towards the bottom and sort of positive towards the top. It's just taking those two features in. It's getting a weighted sum. Remember, that's what I was talking about with perceptrons. You're getting the weighted sum, and then from there you're feeding it into a perceptron, which goes to this final next perceptron, which gives you your output. And so linear relationships, single perceptron, no problem. They got it. It's simple. But then not all problems in the world can be solved with just linearly separable data. In fact, the vast majority of complex problems are not linearly separable at all. They're very messy and they're very dirty. Like, for example, this data set over here, you can't not draw a single straight line to learn this data set properly. If we try to use the same old single perceptron, it's just going to try its best to fit to one corner, but it's never going to do a good job because this architecture wasn't meant for the kind of data that we're feeding into it. However, here's the interesting part. let's just say I were to add another neuron over here. Suddenly, these two perceptrons have the ability to draw two lines. But now here's what's even more interesting. Let's say we add another layer of perceptrons. So the original inputs go to two perceptrons, which feed themselves into another two perceptrons, which feed themselves into the output. Now it can manipulate those lines in more complex ways and create curves. So for example, when you click train now, give it just a moment, and it should usually fit to a better version of the data. Sometimes we want to retry that. Again, the initial random seed that you use to train the network does have a say in how well the network's going to learn. And of course, if you like, you can continue to model even more complex relationships. There we go. So you can just add more neurons, and suddenly it's able to model more complex relationships. So in this case, it was able to draw that sort of curve around the orange boxes and separate them from the blue territory. Now, the only reason this is possible is because of the fact that we're using multiple layers with multiple perceptrons in each layer. So they're able to modify the way that they activate in these really sort of complex ways that couldn't be done with a single perceptron. And I feel like there's a certain analogy to be had in the world of topology that I feel like is truly very valuable. And I know it might seem weird. I'm going to stop sharing my screen for a second so you can actually see me. And there are two items that are incredibly useful when talking about deep learning technology. And those are, first of all, coffee cups, so little coffee mugs, super simple. That's really useful. And also donuts. Right? Donuts are incredibly useful to understand machine learning technology. And I know it might not seem like it, but these two objects are topologically the same, right? So this coffee cup, this donut, they're topologically the exact same. Why is that, you may ask? Well, think about it like this. How many holes does this coffee cup have? Right? You might say there's two, right? Because there's one on the top and then there's the handle. But there's actually just one. And that is the handle, because this one is the through hole, right? You could just move this bottom bit up if this were like rubber, and you could technically mold this coffee cup, if it were made out of like clay, into a shape like a donut, if it worked like, at least. And here's the thing. In order to do that transformation, you wouldn't require any cutting or gluing. And that's not allowed. So the fact that you don't require that means that these two objects are topologically the same. So what that means is you could run a series of transformations on this coffee cup without that gluing or stitching or cutting, and you could turn it into a donut. Why is that significant? Well, it's significant because let's just say I were to take this coffee cup and I were to draw a bunch of dots on it. So they could be dots of two different colors, blue and orange. Now, let's just say that on this coffee cup, you couldn't draw a straight line to separate those two colors of dots because they're all sort of intermingled with each other. But after the stretching and the the transformation into the new shape, the donut shape, suddenly now you can. It's possible that after that series of transformations, the data becomes linearly separable on that new shape. So technically, the topology is the same. You just ran a series of transformations. But in this one representation of that topology, the data wasn't linearly separable. Whereas in this new representation of that same topology, it now is linearly separable. And so, in a way, you can think about neural networks as doing this. They're taking complex shapes with complex data, like a physical analogy could be a coffee cup. And they are learning a series of mathematical transformations that will enable them to convert it to a simpler shape where the data is linearly separable, where the final layer can just do a simple few lines, and just like that, it can understand its data. So if I were to present again my screen like so, then if we were to go back to the TensorFlow playground, you could think about it like these three neurons outputting linearly separable data that this final perceptron over here is just drawing a couple of lines within. And that emergent behavior looks like a curve in the original sort of input space, whereas in this space, it would just be a bunch of straight lines. And so that's a way that you can think about this world of deep learning technology. And technically, this is stuff that I'm going to be getting into in the next episode of this series, but I do want to give you a bit of a sneak peek. And that is an implementation of this concept that I was talking about on the iris dataset. The iris dataset is a dataset of flowers where there are 4 different features captured per flower. Each feature is something like, for example, petal width or petal length. And based off of those features, you want to classify among 3 different species of flowers. Now, of course, there are 4 features, and in a 3-dimensional world, we cannot visualize 4 dimensions. And so I've gone ahead and done a principal component analysis, a PCA, to reduce 4 dimensions to 2, so I can plot out the 3 different species of flowers. As you can tell, one of them is linearly separable from the other 2. So that's trivial. That's super easy. But then the other 2 are really mixed up, and if you were to draw a straight line between them, you would butcher your accuracy counts. And no matter which way you were to do it, this way or this way, you simply would not have good accuracy. But when I train the neural network to do that classification, and I take the output from its last layers, and I visualize that output, you can actually see that the neural network went from this complex shape to the same topology but a different shape where the data is a lot more linearly separable. So if you were to draw a straight line, maybe you would have a sample or 2 that's classified incorrectly, but it's much better than almost all of your samples being classified incorrectly. And so that's what the neural network is doing. It's transforming that data through its hidden layers to go from complex data that doesn't really look like anything to this easy data where the classes are in their own clusters, and then you can use those clusters to predict values. And so that's what the neural network is doing internally. That's what gradient descent ends up learning. However, we will be talking about that in greater depth in the next episode of this series. I'm excited for that for sure. And another thing that I wanted to quickly leave you with is just to show you some of the emergent properties of this fascinating deep learning technology. There is a deep learning system called BERT, developed by Google. And BERT is a neural network that essentially tries to learn generic embeddings for language. So, for example, the same neural network can be fine-tuned and applied to question answering or co-reference resolution or sentiment analysis, whatever, but it's the same basic pre-trained model that's then fine-tuned on those tasks. And the way they train that initial model is by doing something called a fill-in-the-blank task, where they take a sentence and they remove 15% of the words and they replace them with just a mask token, and they have the neural network predict what those masks are supposed to be, or what those masks are based off of the previous and the following context. And so what I did is I trained a similar model, but at a much smaller scale, so it's something that you can actually work with. And this model, hopefully I can actually demo it for you if my SSH connection is still valid or still open. If not, though, of course, I can go ahead and SSH back into it. Hopefully the server is still up. Is it up? It is up. Great. I can actually show you this demo. That's great. So what I did is I trained a very similar fill-in-the-blank model, but this time I trained it on artist names, so musician names. I essentially downloaded a data set of approximately 1.6 million different artist names, filtered it through, got to around 100,000 of them. And then what I did is I trained a model to do fill-in-the-blank for artist names at the character level. So watch this. This is really interesting stuff. I can actually go ahead and run my predict script, and I can give it an artist name. Let's just say Will Smith, right? And I can mask out any character here. Let's just say I remove the S in Smith and I replace it with a mask, which is a capital M. I go ahead and run that, and the neural network tells me that, hey, you probably masked out an S. This final value in the array over here is the prediction that the network made. I think you masked an S, which indeed is correct. We did Will Smith. And there are all sorts of examples that I could show you. I mean, we could take a look at, for example, B. Miller. We replaced the L with an M, and just like that, it says, hey, you masked an L. and it's quite confident in that as well. Now, the outputs here have not been run through softmax activation, otherwise we would get a probability matrix, but that's, again, trivial stuff to do. You could feed in something like Chiara and remove the A at the end and feed in a mask, and it says, hey, you masked an A. And here's a really interesting part. You could even do something like Tanmay. You could mask out the Y at the end, and it might predict a Y. There we go. It's within the top 5. Or if we were to mask out the A in Tanmay and give it a mask there, it says, oh, you've masked out the A. So again, obviously the model is not perfect because I'm not an artist name and it was trained on artist names. There's totally different patterns to them. But again, this model really shows off when you put together those perceptron building blocks. I just want you to understand how amazing that is. Those single perceptron building blocks, when you put them together in more complex architectures and put lots of them together and train them with gradient descent, you can get some amazing emergent behavior. And I cannot wait to explore that even deeper in the following episodes of this series. But with that, though, I would love to transition into the question answering session. If you have any questions, I would love to answer them now.
Again, let's go back to our live Hangout DSEs. So while they prepare, have you built any applications with what you're actually teaching? Anything that practical? I know you mentioned that you built an iOS application a while ago.
So there's all sorts of applications that I'm working on at the moment, actually. One of the most exciting ones is actually a project at IBM that I'm working on. And this project originally was being built for the DB2 org, but is really generic. And essentially the point of the project is there are some code bases with tens of millions of lines of code and hundreds of thousands of test cases. And these code bases are really difficult to maintain. And so essentially what I'm able to do is use machine learning technology, very similar to what I've just shown you, in order to essentially analyze test cases in order to try and figure out the relevance that they have to certain sets of code changes. Now, this requires innovation on all sorts of fronts, not only machine learning for graph neural networks, but also on the compiler technology front, which is where I'm currently most sort of applied, around inventing instrumentation technology that is low latency enough, but still 100% accurate, that it can run in real time on an extremely complex code base with trillions of function calls, enabling it to run at near full performance. So lots of really interesting stuff happening there. And as a matter of fact, before we get to more questions, one more thing that I do want to share quickly is that what I have just shown in terms of that artist's sort of fill in the blank for characters, if you would like to find out more about that technology that I've built, I actually have a talk at the We Are Developers Live Week on the 25th at 12 p.m., where I'm going to be talking about that example and also generally how you can use the BERT architecture with TensorFlow in order to predict the quality of Amazon reviews. And so that's something that that it would be great to have more people sort of join, and if they're interested in seeing how exactly that works. And yeah, so that's how that works, and that's one of the practical things that I'm doing with machine learning technology.
Awesome. So any questions for Tanmay?
While we're on that topic, I was talking about how easy TensorFlow makes people's lives. With TensorFlow technology, what happens is, and the reason that I was talking about that is, if you can imagine an architecture like BERT with its hundreds of millions of parameters, having to manually define the gradient of, for example, the forward pass of a complex neural network is impossible. And with TensorFlow, what you can do is simply define that forward pass, and just like that, internally, TensorFlow will, at full performance, determine a backward pass for you. That's what it enables developers to do. And that's why when it was launched a couple of years ago, it enabled this whole new world of machine learning and deep learning technology. Nowadays, there are quite a few different frameworks that enable that, but still, not only TensorFlow, but even new innovations within the TensorFlow ecosystem, like Swift for TensorFlow, are enabling even better developer experiences. So Swift for TensorFlow, for example, has their sorts of I would say ideologies of how exactly gradient computation and how TensorFlow graphs should be represented. Things have gotten a lot better in TensorFlow version 2, for example. Things have gotten a lot more intuitive and a lot more sensical generally with how things are structured. So yeah, TensorFlow is a pretty great sort of ecosystem and community of software. So any questions around that, I would love to answer them, or really anything that we just talked about. Feel free to ask any questions.
Okay, so you said,
hey,
oh, sorry.
A quick question. Kind of going more on the neural network side, when you were discussing more of the deep learning, I kind of viewed what you first talked about was we were feeding this, how close is your guess to the actual point, and then based off that, it's getting closer and closer. But with the neural network and deep learning, can you kind of talk about more of the components? Because you talked about these, it's just doing a series of transformations, right? We're just trying to see what's the best way to transform it so that we can just make that linear separation. So what are some of like the components that go into helping the neural network determine how to transform or make those transformations?
Sure. So I'm going to keep it really simple for now, and let's just talk again about that iris flower example that I was talking about a moment ago. For that neural network, it's actually essentially the same basic concept that I was showing you with the number negator example. What you've got is you've got some input. That input is fed to the network. The network is essentially just a series of matrix multiplications or weighted sums to calculate the values of perceptrons. Then from there, what you're doing is you're getting the output from those perceptrons, that final layer, and you're calculating the loss. That loss will tell you how off your network is, and you're calculating the loss, the gradient through the loss function with respect to all the weights in the network to adjust them. Now, what I had shown you with the number negator, you only had a single weight, so there was only a single knob that you could turn. But then when you have a more complex neural network, like for example, what I showed you in the network playground, where we had 2 different layers with 3 perceptrons each, that gives you many more individual knobs to turn. But when you calculate the gradient with respect to all of them, you get exactly how each one needs to turn in order to reduce that loss value. So even with more complex architectures, even with the artist sort of fill in the blank thing that I was talking about, it's the same basic structure. You have input, you've got the network. That network can be as deep or as wide as it needs to be. But at the end, you have some output, and you're calculating loss error with respect to that output and calculating the gradient through that loss function with respect to all the weights, and then optimizing those weights based off of that. So that's the basics. Now, there are lots of ways that can be extended in more complex ways in order to make it even better. So, for example, what some folks do, and this is really interesting, they'll actually have 2 separate output layers, where one neural net or where one layer will continue to feed through the network as normal, but it'll also feed to a separate auxiliary network where it'll make a second set of predictions, and you'll try and optimize both loss functions at the same time. And this is to improve gradient flow. Or in order to also improve gradient flow while keeping a really deep network, what you could do is you could do these things called residual connections, which Microsoft introduced a little while ago, essentially having it so that after every layer, you add the value from the previous layer to make it so you're not losing information over time because your network is too deep. In terms of what the network ends up learning, however, is that with gradient descent, again, I would say it really depends on the architecture. So let me give you some examples. With say a convolutional neural network, which is a neural network that's meant to understand image data or spatially or spatial data. Convolutional neural networks start off by learning lower level features, things like individual edges or boundaries in the first couple of layers, because those are very easy to detect. You will need a couple of linear transformations to detect those. But then the layers further down in the network are able to start piecing those together into more and more complex patterns, things like curves or individual shapes, and then into individual objects, things like this. And the thing about how these are trained is we're not training them to learn specific attributes in any layer. All of this is just an emergent property because gradient descent thought that's how exactly it should learn in order to minimize loss. So what it's learning is not based off of any human intuition. It's not based off of any human given logic. It's really more of mathematically these weights should be these values. We don't know why. It's just the gradient value, the gradient function tells us to move in this direction. That's why we're moving. So they end up learning properties that we can perceive as edges or shapes or objects, but essentially it's just the gradient descent is finding the patterns that it needs to find. Things like BERT, for example, that I was talking about in terms of neural networks, has these things called attention layers, where it essentially tries to say, in the next layer of output, what are the inputs that I want to pay most attention to for each output? And you see some really fascinating emergent behavior there as well. So, for example, some attention layers will just automatically learn that maybe we should take the previous word and have it attend to the next word in the sequence, so we can learn what sequences of words mean. And these are things that were not hard-coded, but rather came about as a property of the optimization that was done. And so that's sort of how the training is done, even at large scales, even when it comes to these hundreds of millions of parameters. The same basic framework is still followed, and that's why frameworks like Keras or TensorFlow are so useful. It's because that sort of framework and a lot of the ceremony around it is done for you, and you can just focus on how you want that network to be structured. Structuring it in ways where we believe, or we have some sort of intuition to believe, that it'll learn the patterns we want it to learn.
Awesome. Thank you, Danny, for the question. So we have some questions from YouTube now. Maxim asks, what advice would you give to a beginner who wants to learn machine learning over the summer?
Sure. So, I mean, there's, again, as I mentioned, there's all sorts of ways you can get into machine learning, and it really depends on what you want to do in the future. If you would like to get into the world of machine learning solely for like a single use case for something that's already pretty common, then you could easily use services like Google AutoML to get into machine learning pretty easily. But then from there, if you wanted to get into the, if you wanted to research machine learning technology, if you wanted to become like an expert in this field, then I would recommend starting off with resources like CognitiveClass.ai. They have a bunch of free courses on machine learning technology. I've worked on a couple of them. For example, there's a course of mine on Swift for TensorFlow and game playing AI on Cognitive Class. And essentially what Cognitive Class will enable you to do is understand all the way from basic programming to the math behind machine learning and how it works and how you can use it in different frameworks, things like this. And so I would recommend even following along with this webinar series. Sort of go back, and again, this is available as a replay of it after. So just go back in today's webinar and take a look at the math that I was talking about. See if you can understand that, understand what I was talking about. Implement it for yourself. Try and challenge yourself to solve some problems. And I feel like that's a pretty effective way to learn. And of course, there's also my YouTube channel. So my YouTube channel, Tanmay Teaches, has a bunch of different tutorials on this world of machine learning and AI. So that could be of use as well.
Thank you, Maxim, for the question. Next, we have Sheldon Sebastian from YouTube. If you want to deploy TensorFlow models in production, how would you recommend doing that?
Sure. So I feel like it would be great to be a little bit more specific than just production. So in terms of actually deploying TensorFlow models to production, there's multiple different answers I could give. For example, the one that I would usually do is because my main development environment for front end is iOS. So what I would usually do for a TensorFlow model is export it to a format like CoreML, and then be able to run that directly on device. However, in cases where you have, say, a web application, what you would do then is you would implement, let's just say, TensorFlow.js in order to run TensorFlow directly within the browser in a high-performance capacity to run machine learning on the user's device. In a lot of cases, however, it's useful to run your machine learning on the cloud. So, for example, let's just say you're Google and you're trying to do Smart Compose. Obviously, you're not going to run your neural networks on people's devices because that would take way too much energy. You're going to run back in your data centers. And to do that, you would just wrap your TensorFlow models in, say, a REST API in order to enable you to make those decisions quickly and on the cloud with your hardware that you know is meant to deal with inference. So if there's any like specific model or specific use case that you're thinking of, feel free to send that back in the chat, and I'll definitely get a bit more specific as to how exactly you can deploy that kind of model. But in general, I would say it really depends. There's all sorts of ways you can deploy to production. And that's just even for TensorFlow. I mean, even generically, how you deploy machine learning in production is its own sort of topic altogether around the different challenges of getting machine learning to work in a production environment. But if you were talking about TensorFlow in specific, that's sort of the direction I would think in. Do you want it to run on the edge or on the cloud? If so, what frameworks do you want to use? TensorFlow Lite or TensorFlow.js to stay within that community? Or do you want to go Core ML for iOS? So there's all sorts of things you can take a look at, but that's sort of the general overview that I would give.
So along those lines, Tanmay, one question I personally have is I have to deal with a lot of data, but then cleaning it up, prepping it. So for example, your example with the artists, the data was already available. I think I ended up spending a lot more. Any tips, any tricks, anything that you can share with the rest of them? Because for it to be a practical problem, you got to really find the data and then train the model and then verify it. Anything you can share on that area?
Totally. And again, I feel like in the world of machine learning, it's very difficult to generalize because what machine learning is meant to do is it's meant to make technology more personal. But still, if I had to generalize, I would say that let's take the example of image data. And also, just even before we get into that, one thing that I will say is that it's very useful in machine learning to get creative when you're thinking about how to work with your data. So let's just say in the world of images, you're dealing with, let's just say, noisy image data. Then you can start taking a look at, say, exotic architectures like spatial transformer networks, I think is what, spatial transformer networks. And those spatial transformer networks, what they can do is they can actually take image data, and instead of the neural network just predicting an output, they can predict an intermediary output, which is fed into the network or into the STM in order to crop or transform the image in a way and then come up with some sort of output. So you can take a look at different exotic architectures to deal with messy data. Or you can take a look at pre-processing pipelines that already exist. For example, Keras has this entire image data generator sort of suite of tools that enable you to do all sorts of things around data augmentation. So being able to automatically mirror or rotate or blur images to generate new data in an artificial way that technically is different, although is correct data that you can use to train your models and have them generalize better to your testing. But then what in the world of images, this is pretty standard stuff, right? You can go online, you can search it up, you can find ways to do that. But then when you're working with language is when things get really difficult. I remember a solution that I came up with a little while ago for a similar problem that I was facing. I didn't have enough data to train my sentiment analysis neural networks because it was on a custom data set that we were building. And so the way I solved that problem was by taking a neural machine translation system that I had trained on very little data for very little time, such that it worked, but it wasn't perfect, right? You could go from English to French back to English, and you would get something that means the same thing, but wasn't worded the same way. And what I did was I essentially took my input data, fed it through the model to get French data, and then went back from French to English. And what that let me do was create a brand new sentence that meant the same thing, but was worded slightly differently. And so you've got to get creative when it comes to this. It depends on the use case. For example, for my use case, sentiment analysis, it worked. But for something else, like personality insights, it wouldn't work at all because syntactics are very important. So I would recommend, if you are working on something where the solution is already sort of known, so if you're doing things like regular old image object detection or recognition, then there are lots of sort of pre-built APIs and pre-built tools to help you get started. If not, then getting creative is really important.
Awesome. Going to take another question from YouTube. Aditya Suri asks, I work on research at my university designing machine learning solutions, but one of the biggest things I struggle is picking a project and going. How have you picked your projects? So I'm guessing, like, what kind of tips would you have when you try to pick a project? Sometimes it might not be a machine learning project problem. Yeah. What kind of tips can you share with us?
So personally, for me, the way that I choose problems to work on really is essentially through what do I believe I'm most passionate about or interested in. So it could be, for example, that I'm passionate about solving problems in the fields of healthcare and education, and because of that, I will choose to work on projects that enable me to, work in the fields of, as I mentioned, healthcare or education, enabling people to learn better or enabling people to, save their lives with the power of technology. So that's one way of choosing projects. But another thing is, a lot of my projects that I work on are sometimes even purely as examples to really get across the point of how a more complex system works. So for example, BERT. It's really complex and nobody really has the resources to train it themselves. And because of that, because nobody really does that pre-training, a lot of people just have this cursory understanding of how BERT works, and nobody really knows what goes behind it. So with this artist example that I've come up with, I've been able to create a system that works the exact same way as BERT, with the same positional and segment and token embeddings, with the exact same self-attention networks. But at the same time, it's so much simpler that you can still understand the way it works and run it on your own technology. So that's one, again, the reason I worked on that project was because I was passionate about enabling people to understand the way tech works. So I would say that really work on something that you're fascinated by, because when you're fascinated by it, when it piques your curiosity, then that perseverance just comes automatically, right? This artist neural network, for example, obviously didn't work on the first try. It took many, many different attempts to get it to finally work. But when you're passionate about something and when you want to see something working, that perseverance just comes automatically.
Awesome. Anybody from Hangout want to ask any questions? Have any questions? If not, we can go back to YouTube.
I got a quick one if no one else does. A kind of continuation on my last question.
Awesome.
So you discussed the gradient and how we are using that. So I just kind of want to understand, right? So we have this model, let's say, like going back to the example you gave with detecting objects, let's say. So we start off with something really simple and hope that our gradient pushes the model in the correct direction that we're expecting it, right? Yeah. We don't want the person creating the model to do it. We want the gradient. So what are ways that we can kind of better build that gradient to kind of make, not guarantee, but help us have a better probability of getting the outcome we want?
Sure. So there are multiple different ways, but there are two main ones that I'm going to focus on right now. And that is that, first of all, the way you create your neural network is important, not in terms of structure, but remember, the initial weights that we start off with are random. And when you choose better initial random weights, that means there's less work for gradient descent to do to get you closer to a better local minimum of the loss function. And so choosing a good weight initialization strategy is definitely important. And that varies from use case to use case. Most use cases just do random uniform initialization, and that works really well, right? Because gradient descent is able to find that local minimum pretty easily because it's such a robust technique. However, there are lots of use cases where that doesn't work. So for example, there are these things called mixture density networks, where the network actually tries to predict parameters of a probability distribution that is then sampled from. And when you're using mixture density networks, then you want your mixture sort of network to not be initialized with a uniform random probability, but rather a truncated normal initialization with a certain standard deviation around 0.07 is like one of the optimal hyperparameters. And so weight initialization is definitely one of the best ways to help gradient descent by putting it in a better place, on the spot right as it gets started. So it needs to do less prep work. And by doing so, you reduce quite literally the surface area for error. But then, if we take a look at a different example, I would say that standardization of data really helps. So when it comes to gradient descent is a lot better at learning if the inputs to your network and generally the values within your network are centered at 0. So if they have a mean value of 0 and a standard deviation of 1, that's great for gradient descent. It's a lot easier for gradient descent to work that way. And so what you would usually do with a network is you would take all the inputs and all the features, you would calculate the mean value for each feature, and you would calculate the standard deviation, and you would negate the mean and divide the standard deviation to do that 0 centering. But nowadays, we have these new innovations called batch normalization and layer normalization, which enable you to do standardization within the network as well. So within like the intermediate outputs of the network, you can run that standardization per batch. And the reason that is so great is because gradient descent has so much of a better time learning. I actually have a tutorial on batch normalization. It's really impressive to see just how much faster the neural network learns in 2 epochs with batch normalization versus 10 epochs without it. And so those are 2 techniques that do help gradient descent, although I will say that in a lot of cases for basic things like what you mentioned around image recognition, you don't really need to help gradient descent that much. It does well with just a regular uniform random initialization of the weights. It does well without batch normalization, but these are things you can do to augment that gradient space to help it out. Also, just really quickly, I did mention residual connections. Residual connections are also one of those innovations to help gradient descent. So what happened was eventually when networks started to get too deep, when neural networks started to get too deep in terms of layers stacked one on top of another, the network would just lose information on the way, right? It would not be able to learn to keep relevant information throughout each layer because there were simply too many transformations happening. And that was a problem because in theory, you would think that the gradient descent algorithm would just be like, okay, if I don't need certain transformations, then I'll just learn an identity function and just return the previous layer's output. But in practice, that never really emerged because, again, it was too deep. But then what Microsoft came up with was a solution which was inspired by highway networks, which is just take the previous layer's output and add it to the next layer's output, and just like that, gradient flow is a lot smoother. In fact, if you were to actually visualize the gradient space of a ResNet versus like a VGGNet or something that's less but doesn't have those residual connections, you see a much smoother gradient space. And when it's smoother, you don't have jittering and oscillation. So there's all sorts of things you can do to help out your gradient descent. In general, standardizing your data and using a better initialization are 2 things that immediately help, and then you can always stack more things on top of that.
Thank you, Danny, for the question. This is great. I'm assuming you're good to take a few more questions, Tanmay?
Oh, totally.
Okay.
I would love to answer questions.
We're going to take another question from YouTube. William asks, hi, Tanmay, I'm a game developer. What kind of features could you expect machine learning to help with video games, AI, NCPC? So a simple example he gave is would realism, but I wanted to know if you had ever thought about this area. So it's more like a thought leadership question.
Yeah, absolutely. And I feel like deep learning in gaming actually has a lot more of an effect than a lot of people would think. And we've seen this with multiple different examples. Remember, machine learning is the kind of technology that impacts every field and every domain of every field. So within gaming, AI is touching everything, all the way from game design to game development to actually running the games on hardware. And I want to get a little bit deeper into that. For the longest time, complex games, like strategy games, for example, have been kind of cumbersome to develop AI for. I wouldn't even say that. They've just been outright terrible to develop AI for. And either you end up with an artificial intelligence that's so dumb that humans easily win against it, and there's no point in even having the AI in the software, or you end up with AI that's so immensely overpowered because the game designers give it access and control in ways that humans could never have. And with the power of machine learning technology, you can really start to create players that feel a lot more human than any human-designed AI could. So we've seen this with multiple examples. The game of Go is a perfect one. Previously computers would essentially barely ever be able to challenge a human player. I mean, you get past, I believe, the one dawn barrier, and after that, humans, are instantly masters of the game. But now, with the power of AlphaGo and AlphaZero and these new technologies by DeepMind, we're starting to see computers reach levels that humans could never have even conceptualized, and now we're starting to see technology playing Go at not only superhuman levels, but we're starting to see supercomputer levels in more and more systems. So that's one of them. That's, again, game AI. That's one of the obvious ones. But then from there, there's also the experience of playing the game itself. For example, ray tracing is pretty huge. I mean, with ray tracing, NVIDIA has enabled us to have this sort of lifelike experience within games. And obviously, we don't have the compute power to do actual ray tracing. So they do this thing called DLSS, or deep learning supersampling, where they use machine learning to predict what light rays would do, and to make it more computationally feasible. And so machine learning is really being used across the entire sort of spectrum. And I even mentioned game design. We're starting to see OpenAI came out with their new neural network around generating art, things like music and images and things like this. And that can obviously be used for, even if not directly generating assets for games, at least inspiring the game designers for those assets. So I would say every domain, the entire spectrum of the gaming community is going to be impacted by machine learning technology in at least some way.
For example, like the ISP, internet service providers, are looking into things. So there are no lags when it comes to connecting people. Let's take another question. I think I'm going to combine two questions together here. Sheldon asks, which are your favorite books to learn neural networks? And TensorFlow and DB123 asks, as a total beginner, where can he start? What kind of things he can practice on to reinforce his concepts and start building small projects? So I know you have a few books listed right behind you. Let's start with that.
Yeah, sure. So you mentioned books. I do have a couple of books that I've written. They were published just last year, so you're seeing them behind me. I'll get a physical copy in a moment. But they're Hello Swift, Cognitive Computing with Watson, and Tanmay Teaches Julia. Tanmay Teaches Julia in specific is meant to get you into the world of programming and then into the world of machine learning from there. And so those would be some of my favorite books to get into the world of machine learning. But then from there, let's see. I'm gonna have to think about some other books around machine learning, because usually the resources that I use are online. So as I mentioned before, there's cognitiveclass.ai. That is a great platform. I've personally worked with a lot of people that have written the courses behind that, and I can vouch for the sort of quality behind them. And I've written a couple of them on that platform as well. So for example, a course on Swift for TensorFlow and game playing AI, where we cover all the way from Monte Carlo tree search for 2048 to reinforcement learning, to play cart pull, and Minimax for tic-tac-toe. So from simple to more advanced examples. And then, of course, if you're talking about a little bit more complex machine learning technology, I did mention my Julia book. And there's actually an example that I want to show you over here. Give me a second. Right, so I took a picture of myself, and I implemented the Google Deep Dream algorithm. And you can kind of see over here that with this book, you can actually generate sort of like machine learning generated art with the power of neural networks by using gradient descent to modify the actual image. So with the Tanmay Teaches Julia book, you can learn how to do like deep dream and more advanced machine learning, although this is in the Julia language and not in the TensorFlow framework. However, the same concept obviously applies to TensorFlow. And so I would say that the best ways to get into it, as I mentioned, the books that I've written, my YouTube channel, Tanmay Teaches, and webinars like this one, definitely follow along with the series. This is going to help you get into the world of machine learning. Once again, rewatch this, understand the math that I was talking about, see if you can try and get that. And also cognitiveclass.ai is a great way to get started as well.
Okay, so one last two questions. What are your thoughts about working with imbalanced data?
Imbalanced data.
How does ML find the needle in the haystack?
Sure, sure. So again, there's all sorts of ways to do it, I would say, but there's one specific sort of technique that I've been working on developing for a couple of weeks now, and this is actually something that I'm going to be covering in my talk at We Are Developers on Monday. And basically, it's not meant to deal with severely imbalanced data, like some of the kinds of data that we have, but rather dealing with a general imbalance in data where we want to run a regression problem. So in regression, imbalanced data is generally a much larger problem than it is in classification, because in classification, you can quite easily apply a weight to the loss function, and that usually solves the issue for mildly imbalanced data. But then with regression, it's not as simple. And so what I've essentially done is sort of worked on incorporating regression into a technique where the model doesn't learn the continuous values directly, but rather learns the relative differences between those continuous values for two separate classes. So for example, if I wanted to take Amazon reviews, instead of feeding an Amazon review to the model and having it predict quality as a continuous value, I would leave the activation as unbounded, so just a linear activation. And I would actually run the network twice and take the same outputs, concatenate them, run softmax, and then treat it almost like a classification problem. So I would treat the network, I would actually train the network to learn that point-wise ranking, that continuous value based off of pairwise relative data. So that's something that I've been working on, and you'll hear more about it in the We Are Developers talk to see some actual metrics on how it performs. But yeah, do join that. It's on the 25th at 12 p.m. EST, and I'll be talking more about that then.
Awesome. One last question, and this is from me. It's easy to learn as a group. It's easy to learn as a community. That's why we have developer student clubs and Google developer groups and things like that. Mm-hmm. Now, even when you're in university or school, you can get into a study group. Any suggestions, any platforms, any tools that you can recommend? So let's say somebody gets stuck, they don't want to ping you all the time. Is there a place that they can go ask their peers as to how they can collaborate on something? Any suggestions, any tips you can share?
Sure. So there are all sorts of ways to learn with the community. I mean, one of them is the more obvious one, where when you encounter an issue, you would go to places like GitHub or Stack Overflow in order to get answers to your questions, or in order to sort of interact with the community. But of course, there's sort of better ways that you can interact with the community itself. So, for example, you can go to websites like DevPost, and you can find, for example, hackathons. I was just mentoring and had a keynote at the Teens Take on COVID hackathon, actually, which if you were to go to DevPost, you would be able to find and join pretty instantly, and you would just be able to start working with the team at the hackathon and learning with the people and the mentors from that community. That's definitely a great way to learn, especially in times like this one, where everyone's doing this stuff virtually. It's a great time for anybody from across the world to participate in such events. Then, of course, there's other sort of communities, like, for example, the Google Developer Expert community, which is there to help people that want to work with these Google products, things like TensorFlow, Google Cloud, whatever it is. Google Developer Experts can help you. So they're definitely like a good group of people to reach out to get the answers to your questions, or to figure out more about this technology. Apart from that, I would also say that generally, when it comes to learning as a community, going to resources like, for example, as I mentioned, GitHub, and just being able to take a look at code that others have written, and being able to base and really derive inspiration and insight from that code is really important. I found that a lot of my applications start off as essentially trying to replicate the results as a baseline that I get from paper or a GitHub repo, and then from there evolving it to something completely different. But it's always useful to have that baseline. So when it comes to community contributions, that's a great way to get started. So there's all sorts of ways, right? You could ask questions on Stack Overflow, you could participate in hackathons, you could ask communities like the Google Developer Expert community, and really these are all great ways to interact with the community.
Tanmay, thank you so much for taking the time. This has been amazing. the engagement has been great, and we would love to get you back and kind of set up the second stage of this series and see where it goes from here.
I would.
And yeah, for sure. So what we're going to do is we're going to share all your events, the upcoming events here, as well as your YouTube channel. So anybody who has other questions and any other sessions they want to learn, they're more than welcome to go and engage with the content you have. That being said, for those who are listening, thank you so much for joining. Thank you so much for engaging with us. Thank you for sharing with your communities. If you've already done so, we're going to come up with at least 1 or 2 events a week, and we're going to keep you posted. So stay tuned, follow us on Twitter, subscribe to the YouTube channel, and if we already have your email addresses, we're gonna ping you and let you know. So that being said, I'm gonna wrap this up, and once again, thank you so much, and hope to see you again soon.
Sounds good. Thank you very much for inviting me. Glad to be doing this. And again, if you have any questions, feel free to reach out to me as well. I would love to answer them. And yeah, thank you very much. Can't wait for the next episode.
Awesome.